In this video, we're going to determine the pH of boric acid, and it's a 0.5 mole per liter solution of boric acid. Boric acid is, really doesn't actually matter too much what the acid is, but it's H3BO4, I think, BO3AQ, and it's an acid in water, and so it's going to make, it's a weak acid, so it's make a hydronium and dihydrogen borate. Now, so this is the acid, this is the base in the forward reaction, this is the acid and the base in the reverse reaction. This is a conjugate acid-base pair, and this is a conjugate acid-base pair. Just kind of refreshing your memory about a few of those things. But in this case, you have a concentration of boric acid of 0.50 mole per liter. Now, we want the the pH of this. I don't know anything except the Ka of boric acid. Now, this doesn't happen to be in your data booklet. This is provided in the textbook. But it's 5.8 times 10 to the negative 10. In order to predict the concentration of hydroniums and use the formula that the hydronium ion concentration equals the square root of the Ka times the concentration of the acid, in this case boric acid. In order to do this, this has to be a weak acid, and you need to have the concentration of boric acid divided by the Ka needs to be greater than 1,000. And if I take 0.50 mole per liter and then divide it by 5.8 times 10 to the negative 10, this is such a weak acid that it's going to be way bigger number than 1,000. I'm not going to put it in my calculator because it's not really worth it. But at this point, the hydronium is going to be equal to the square root of the Ka, so 5.8 times 10 to the negative 10, times 0.50 mole per liter. And because the change in equilibrium, concentration of borates, or boric acids, is going to be so small, it'll have no impact on this concentration. That's what this calculation is trying to tell us, is that basically it's going to be such a small change that you can't even subtract it from this number. So then on my calculator, I'm going to take the square root of 5.8 times 10 to the negative 10 times 0.50, and it gives me a concentration of 1.7 times 10 to the negative 5 mole per liter of hydronium ions. The pH is going to be equal to the negative log of that number. So negative log of the hydronium concentration. So if I take the negative log of this, it gives me the pH. So I get the negative log of 1.7 10 to the negative 5, and it should give me a pH of about 4. If I can get my calculator to work correctly, that'd be great. So it's giving me a pH of 4.7695. This has two significant digits. pH has two significant digits follow the decimal place. So since it's 4.769, two significant digits gives me 4.77, and that should be the answer for this question. And again, in order to be able to do this, I need to fulfill this. Otherwise, I'd need to use the quadratic equation, which is outside the scope of our curriculum.